In the previous two videos, we've been discussing the method of separation of variables whereby we can convert a partial differential equation, in some cases through separation of variables, into a differential eigenproblem. We illustrate the process for the Laplace equation and the one-dimensional unsteady diffusion equation. Now we're going to take a look at the wave equation. This is a canonical example of a hyperbolic PDE. And let's begin by taking a look at the general situation where we could have a PDE of any dimension, 1, 2, or 3 dimensions in space plus time. So m and k here will be linear differential operators in space, so x or xy or xy and z. And then the dots indicate time derivatives. So u double dot is partial squared u partial t squared. So the solution we're looking for, u, is a function then of x, y, z, and t potentially, or it could just be x and t or x, y, and t as well. And again, we're going to apply the method of separation of variables and show how we can convert the wave equation into ordinary differential equations, to which we can apply our usual eigenfunction expansion approach. So we start by taking the dependent variable, u, and breaking it up into the product of two pieces, phi, which accounts for the spatial aspect of the solution, and psi, which accounts for the temporal aspect of the solution. So you notice in the previous cases we only had two variables, x and y, or x and t. When you have more than one spatial variable here, then we'll combine that all into the phi. So we substitute this into the general form of our hyperbolic PDE, and we have psi double dot times m operating on phi plus psi times k operating on phi is equal to 0. Again, remembering that the m and the k differential operators only have spatial derivatives in terms of x, y, and z, no time derivatives. And then the question is, can we put all the spatial information on one side of the equation and all the temporal material on the other side of the equation? And we can. So k phi over m phi is equal to minus psi double dot over psi. And because we can separate the spatial and the temporal dependence, that then tells us that we have a separation constant lambda, because we can vary x, y, and z and t independently of one another. Then that allows us to convert our one partial differential equation in both space and time into a differential equation for space and a separate differential equation for time. Now in this case, the time equation will be an ordinary differential equation, whereas the spatial equation could be ordinary if there's only one independent variable in space, say x, or partial if it's xy or xy and z. So we have those here. So k phi is equal to lambda m phi. You can see clearly that that is a differential eigenproblem, but of a partial differential form. And then we have psi double dot is equal to minus lambda times psi, which is an ordinary differential equation. So again, the spatial information is accounted for in the phi equation, and the temporal information is accounted for in the psi equation. Now in the previous two cases we've looked at, Laplace's equation and the 1D unsteady diffusion equation, the eigenmodes and the eigenvalues didn't have any physical connotation or meaning. They were merely a mathematical construct by which we could apply the separation of variables method and get a series expansion for the solution. Here in the case of the wave equation, now the eigenvalues as well as the eigenfunctions are going to have a physical meaning, and that is the following. So the eigenvalues themselves, the lambdas, are going to be related to the natural frequencies of vibration of the system. And the eigenfunctions, the phis, then, are going to be the vibrational mode shapes. So if you imagine plucking a string, there's the shape of the string, and that's made up of an infinity of spatial modes or vibrational mode shapes. Those are the phis, of which there'll be an infinity of them. And then the time dependence of those infinity of spatial modes, depending on the initial conditions for the system, will determine how much of each mode at any given time. So once again, in the wave equation context that we're looking at here now, the lambdas and the phis have physical meaning as well as mathematical meaning. So let's take a look at the 1D wave equation first. Partial squared u partial t squared is equal to c squared times partial squared u partial x squared. The c here, that's the wave speed, so how fast a wave moves in this particular medium. And you'll notice this is very similar to the unsteady diffusion equation, except now we have a second order derivative in time rather than a first order derivative in time. But that changes the whole character of the equation. It's now hyperbolic instead of parabolic, and the types of solutions we get are completely different. In the case of a vibrating string, so think of a stringed instrument such as a guitar where you pluck the string, the c squared is equal to capital P over rho. Capital P is the tension on the string, and then the rho is the mass per unit length of the string. It's like the density of the string. So that's the image that we'll have in our mind. Now in the general three-dimensional case that we looked at the beginning of the video, the m will be minus 1 over c squared, and the k will be partial squared partial x squared. That's the only spatial derivative that we have in our 1D wave equation. Notice the c squared, we could put it in the m or the k, it doesn't matter. I put it in with the m. And then the equation for phi that we have is d squared phi dx squared plus omega squared over c squared. Phi is equal to 0. This omega squared, that's always going to be positive, and that's our lambda. So I'm using omega here to indicate a frequency, whereas before we used a mu. So it's the same as the mu that we used before, but because it's a frequency, we'll call it omega. So that's the equation for phi as a function of x. And then the equation for psi as a function of t is d squared psi dt squared plus omega squared psi is equal to 0. Now we'll need two boundary conditions in x, as well as two initial conditions in psi. So let's start by writing down the general solutions of these, and then we'll talk about initial and boundary conditions. These are both second order linear, constant coefficient ODEs. The solutions are cosines and sines, and you can see that it's just the square root of the coefficient on the phi or the psi term that's inside the trig functions. So let's focus on this one first, the phi sub n of x. These are the spatial mode shapes. These are the eigenfunctions of our differential eigenproblem. And remember that the eigenvalues, the lambdas, are omega squared over c squared in this case. All right, so we need two boundary conditions and we need two initial conditions. Let's talk about the boundary conditions first. Let's say that they're both homogeneous. So the value of u, the displacement of u, is 0 at x is equal to 0 and 0 at x is equal to L. So both ends are fixed. The displacement is 0 at both ends, so they're homogeneous. And remember, the boundary conditions are on u. We need them for phi. So at x is equal to 0, u is 0. In order for that to be the case, because u is phi times psi, phi at 0 has to be 0. You substitute that into 373 up here, and that requires that c1 be 0, because that's the cosine. Cosine of 0 is 1, sine of 0 is 0, so we have to get rid of this term. In order to do so, we set c1 is equal to 0. Then on the other side, u at x is equal to L is also 0, so that requires that phi at L also be 0. And then from here, because this term is already gone, this term, sine of omega over c times L, we're applying this at x is equal to L is equal to 0, becomes our characteristic equation. And as we've seen before several times, this argument on the sine has to be equal to an integer multiple of pi. So omega times L over c has to be an integer multiple of pi. So therefore the omegas, which are related to the eigenvalues, and they are the natural frequencies, are n pi c over L. So you'll notice that the wave speed influences the natural frequencies of vibration. The eigenfunctions then, we only have the sine term. Remember, c1 is 0, so we only have the c2 times sine of n pi over L times x term. For now, let's just choose c2 being equal to 1 for convenience. Okay, so we have our eigenfunctions. Those are the phi sub n of x's. They are also then physically the vibration mode shapes, or we can refer to them as basis functions, because they're going to be the functions that are going to form the basis for the solution of the vibrating string. And they're Fourier sine series. So you can see here the phis, the mode shapes are just sine functions. So it's a Fourier sine series, of which we have an infinity of them, as usual. Now if you think back to chapter 2, where we had discrete systems, we had n degree of freedom problems, and the number of natural frequencies was equal to the number of degrees of freedom. Here we have continuous systems, such as our string is a continuous system with an infinity of points between 0 and L, and so it now has an infinite number of degrees of freedom, and therefore an infinite number of natural frequencies, and those are related to all of the lambdas. Okay, so that's the boundary conditions. Now let's talk about the initial conditions. Remember, we need two now because it's a second order equation in time. So the first will be the initial displacement. So that'll be a function of x that shows the shape of the string at t is equal to 0. And the second initial condition will be an initial velocity. So that's partial u partial t, or u dot, at t is equal to 0 is some known function g of x. So those are the two initial conditions. Now, given those two initial conditions, we can then look at our solution for psi. We already wrote this down. Psi is c3 cosine omega t plus c4 sine omega t. We now know omega from the solution of our eigenproblem. It's n pi c over L. In order to accommodate the initial condition on velocity, we're also going to need the derivative of psi with respect to time. So that's psi dot. So if you just differentiate this, you have omega times sine omega t and omega times cosine omega t. So if we put in t is equal to 0 to the first one, then psi at 0, well, sine of 0 is 0, cosine of 0 is 1, so psi of 0 is c3. If we put t is equal to 0 in this expression, then we have psi dot at 0 is equal to, now this term goes away because sine of 0 is 0, and this term cosine is 1, so that's c4 omega n. So we can substitute these back in for c3 and c4. So that gives us a replacement for equation 378. Psi of t is psi at 0 times cosine omega t plus 1 over omega times psi dot at 0 times sine omega t. And it still remains to determine expressions for the psi at 0 and the psi dot at 0. There's an infinity of them because n goes from 0 to infinity. So let's talk about how to get those. So we have our initial conditions. U at t is equal to 0 is f of x, and u dot at t is equal to 0 is g of x. So through our separation of variables, we have that u is phi times psi, but now psi is at 0, and that's equal to f of x. And u dot is phi times psi dot, again evaluated at 0, that's g of x. Just as we've done before, we take the inner product of the eigenfunctions with each of these two expressions, and they give us an expression for psi sub n at 0 and psi sub n dot at 0 in terms of inner products of f and g with the eigenfunction. So you can see these integrals here. They look very similar to what we had before, but now there's two of them. And they are the Fourier sine coefficients of f of x and g of x. Again, very similar to what we had before. So we put this all together. U as a function of xt is the sum of the phis times the psi's, where again the phi, those are the spatial mode shapes, and the psi's take care of the temporal dependence. We know the phis, those are the eigenfunctions, those are sines of n pi over L times x, and then the psi is this expression here, which is straight off the last slide. The omegas, which are the natural frequencies of vibration, and related to the eigenvalues, those are n pi c over L. Okay, so let's take a look at a specific example. Let's say that our initial condition is g is equal to 0, so the initial velocity at t is equal to 0 is 0, but the original shape at t is equal to 0, which is f of x, let's say that that's a Gaussian distribution. A Gaussian looks like this. You'll see what it looks like in a moment. So you put this in for f of x and g of x in here and here. Well, obviously g of x is 0, so the psi dots at 0, those are all 0, whereas the psi at 0, put in f of x is that Gaussian distribution. You do the integration to get the Fourier sine coefficients. Those then complete the solution, and let me show you what that looks like. This is for a length of 1. A is 1, B is 100. Those are parameters within the Gaussian. They fix the width and the amplitude of the Gaussian. And then this is the solution you get. So this is t is equal to 0, the initial shape, and then time is going back and to the right like this. So the initial shape has this hump in it. That's the Gaussian distribution, and that produces a right moving and a left moving wave. They both have the same amount of energy, half of the initial energy in the Gaussian distribution. When they hit the fixed zero displacement boundary conditions on the left and right, they reflect back as waves with the same energy but opposite amplitude. Then they bounce off the wall again, and you can see when they superimpose, you can't see it underneath, but it does the same thing. It superimposes to form actually the same exact shape as the initial wave. There's no dissipation at all, so this just continues on forever in time. These waves bouncing back and forth, superimposing and changing sign and so forth. Okay, that was the 1D wave equation. I just want to quickly show you, I'm not going to go through all the details of this example, they're in the book if you're interested, but I just want to walk you through the structure of how we would solve a spatially two-dimensional problem. And it turns out that this produces the Bessel equation, which we talked about in an earlier video on Bessel functions as the eigenfunctions. So instead of a string, let's think about a circular membrane. So you can think of this as the head of a drum, and the vibration of the drum head then is a superposition of the infinity of mode shapes, the phis of r theta. We're going to do this in polar coordinates. And so we have the wave equation, partial squared u partial t squared, just like before, is equal to c squared, c being the wave speed. And now the second derivative on the right-hand side is going to be the Laplacian in polar coordinates. And you can see those are the spatial derivatives, the r and theta derivatives. Now we've already done the separation of variables. The m is minus 1 over c squared, just like before. But now the k, because of the two-dimensionality, are the r and theta derivatives in the Laplacian, which you see here. The boundary condition will be 0, so 0 displacement all the way around our circular membrane of radius 1. Okay, so this is how this works. Again, I'm not going to go through the details, but let me just walk us through the separation of variables. U here is a function of r and theta, the spatial coordinates, and time. So we're going to actually do kind of a nested separation of variables. The first separation of variables, you separate out the temporal dependence. So you'll have a psi of t, and then the spatial coordinates all get wrapped up in the phi. So phi of r theta. Then you separate the variables. You'll get a ordinary differential equation for psi, and you'll get a partial differential equation for phi, because it depends on two independent variables, r and theta. Then that PDE, you can further separate the variables into a g of r and an h of theta. So again, it's kind of a nested separation of variables. And it's the eigenproblem for g of r that turns out to be a Bessel equation. We talked about Bessel equations a few videos ago in the context of Sturm-Liouville differential operators. So then we solve the Bessel equation for the g of r, we solve for the h of theta. Those combine to form the phi and the psi, which then combine to form the u of r theta t. As you can expect, this will be rather involved. And the details, again, they're all here. You can look in the book. You have to think about the periodicity as theta overlaps on itself. So there's some additional factors that come into here. But here you can see that Bessel equation that we had, and that, again, is for the g of r. Let me just show you what some of the solutions look like. So these are various n and m combinations. Because we did this nested separation of variables, we're actually going to have these two indices, n and m. So the n is equal to 0, m is equal to 1 mode, or basis function, gives us a shape that looks like this. N is equal to 0, m is equal to 2, gives us the sombrero shape. So these would be nice hats to sell on Etsy, maybe. For n is equal to 1, m is equal to 1, you get this interesting shape. 1 and 2, you get this. And again, there's an infinity of these. These are the spatial mode shapes of the drum head. These form the basis for the actual solution, the shape of the drum head at every point in time. Depending on the initial conditions for the displacement and the velocity of the circular membrane, that will determine how much of each of these spatial modes occurs at every point in time as the drum head or circular membrane vibrates. So again, each of these are modes when added up with all the infinity of other modes superimposed to give the solution of the wave equation in the form of this vibrating circular membrane. Let's just finish with a few remarks. So again, just emphasize something I said before. The eigenvalues and eigenfunctions have a mathematical role. And we've seen that in the previous two videos for Laplace's equation and the 1D unsteady diffusion equation. In this context, they have the same mathematical role, but they have an additional physical interpretation. The eigenvalues are related to the natural frequencies, and the eigenfunctions are the spatial mode shapes that together comprise the shape of the vibrating circular membrane. Finally, let's just reflect on how far we've come. At the beginning of chapter 2, we were talking about the algebraic eigenproblem. A, u is equal to lambda u. Talked about applications, we talked about how to get the eigenvalues and eigenvectors. Then we extended that in chapter 3 to how we can solve ordinary differential equations using this eigenfunction expansion approach. Again, eigenvalues and eigenfunctions, now of differential operators rather than of matrices. And then finally we showed how through separation of variables we could extend that same technique to solve certain partial differential equations. In fact, this is really just the beginning. Spectral numerical methods, which are discussed in chapter 7, reduced order modeling, which is discussed in chapter 13. These are all modern applications, very powerful applications of the basic underlying theory that we've just been discussing, solving some very contemporary issues in science and engineering.